This video provides an introduction to inverse matrices. We've talked about inverses before, inverse functions. There's the multiplicative inverse, the additive inverse from our properties of real numbers. So now we're going to look at inverses for matrices. Before we can talk about the inverse, we have to talk about the identity. The n by n matrix with ones down the main diagonal from upper left to lower right and zeros everywhere else is called the multiplicative identity matrix of order n. This matrix is denoted I sub n. I for identity, and the sub n is just what's the dimensions of the square matrix. So here we have some examples of what identity matrices look like. There is the identity matrix of dimension 4 and the identity matrix of dimension 3. Now, we've talked about the identity before when talking about real numbers. We have the additive identity and the multiplicative identity. Identity simply means that it leaves things unchanged. So our additive identity is 0 because if you add 0 to anything, you just get that thing. And our multiplicative identity for real numbers is 1 because if you multiply something by 1, you get that thing. So how does that apply to matrices? If we let A be an n by n matrix, if there exists an n by n matrix B such that their product gives you the identity matrix, then B is the multiplicative inverse of A. The inverse of matrix A is denoted the same way we do inverse functions with that little, looks like an exponent of -1. So there we go, A inverse. We're going to use this property that when you multiply two matrices together and their inverses, then you get the identity. We're going to use that to check whether two given matrices are inverses of each other. Now you'll notice in the definition, since matrix multiplication is not commutative, you actually have to check the multiplication both ways, A times B and B times A. We need to get the identity both times. So let's start with A times B. Checking the dimensions, we have a 2 by 2 times a 2 by 2. The insides match, so we know we can do the multiplication. And the outside numbers will give us the dimensions of the product. So a 2 by 2 times a 2 by 2 leaves us with a 2 by 2. And I'll put in some variables here just to help us reference. And now we'll multiply. Element A is located first row, first column. So we'll be multiplying the first row of our first matrix with the first column of our second matrix. This is going to be 2 times -4 plus 3 times 3. It's -8 plus 9, which is equal to 1. Now remember what we're trying to get here to. We're trying to get to the identity, which looks like this. So if during my multiplication I get any number different than what it's supposed to be for the identity, I would simply stop and say these matrices are not inverses of each other. On to element B, it's located first row, second column. So we'll be multiplying the first row with the second column. That's 2 times 3 plus 3 times -2. That's 0 plus 0, which is 0. All right, looking good so far. The first row of my matrix matches the first row of the identity matrix. Moving on to element C, its position is second row, first column. So we'll be multiplying the second row of the first matrix with the first column of the second matrix. 3 times -4 plus 4 times 3. That's -12 plus 12. which is 0. Still matching up with the identity there. And then our last element, D, it's located second row, second column. So we'll be multiplying the second row of the first matrix with the second column of the second matrix. That'll be 3 times 3 plus 4 times a negative 2. 9 minus 8 is 1. And you'll see with this first multiplication, we do indeed get the identity. Great. So we're halfway there. Now we need to check B times A and see if we get the identity matrix when we perform that multiplication. Be sure that matrix B is written on the left and matrix A on the right. A 2 by 2 times a 2 by 2 is going to give us a 2 by 2. Starting with element A, it's located first row, first column. So we'll be multiplying the first row of the first matrix with the first column of the second matrix. A equals negative 4 times 2 plus 3 times 3. That's negative 8 plus 9, which is 1. Element B is positioned first row, second column. So we'll multiply the first row with the second column. That'll be negative 4 times 3 plus 3 times 4. Negative 12 plus 12 is 0. Looking like the identity. Keep checking, because as soon as it doesn't look like the identity, I would first double check my work and then state that they're not inverses. All right, on to our element C. It's positioned second row, first column. So let's multiply the second row of the first matrix with the first column of the second matrix. C is going to be equal to 3 times 2 minus 2 times 3. 6 minus 6, 0. And lastly, our element D, it's located second row, second column. So multiplying our second row with our second column, it'll be 3 times 3 minus 2 times 4. 9 minus 8 is equal to 1. Notice that we got the identity matrix a second time. Therefore, we can conclude that A and B are inverses of each other. If you recall, we did something very similar to determine whether two given functions were inverses of each other. We did function composition both ways, and if we got x twice, then we knew that they were inverses of each other. It's a very similar procedure happening here. All right, let's check another pair. This time we have a 3 by 3 and a 3 by 3. Checking the dimensions, a 3 by 3 times a 3 by 3, the middles match, and our product matrix will be a 3 by 3. So let's start by multiplying A times B. A on the left and B on the right. We'll start by finding our element A. It's located first row, first column. So let's multiply our first row of our first matrix with the first column of our second matrix. That'll be 2 times 0 plus 0 times 0 plus 1 times 1. That's 0 plus 0 plus 1, which is 1. And remember what our 3 by 3 identity looks like. It's 1s down the main diagonal and 0s everywhere else. So I always like to write that up, so as soon as it doesn't look like that, I can state that they're not inverses. Element B, it's positioned first row, second column. So that's going to be 2 times 2 plus 0 times 3 plus 1 times 0. That's 4 plus 0 plus 0, which is 4. Oh no, we got a problem. Here we have a 4, and the identity has a 0 in that spot. I would not waste my time doing any other multiplication. We can conclude that A and B are not inverses of each other. Please note that only square matrices are eligible to have an inverse. Just like only one-to-one functions are eligible to have an inverse, only square matrices are eligible to have an inverse. If a square matrix has a multiplicative inverse, then that inverse is unique. See, you're not guaranteed just because it's a square matrix that you will actually get an inverse. If a square matrix does have a multiplicative inverse, it is said to be invertible or non-singular. However, if a square matrix does not have a multiplicative inverse, it is said to be singular. The way that I remember these vocab words is I use non-singular and singular. So non-single means not single. So if you're not single, you have a partner. So there's going to be a second matrix, the inverse matrix. But when I see the word singular, I think single. And if I'm single, I don't have a partner. I'm going to be a matrix all by myself. So that's our introduction to inverse matrices.